Now the question is, how do we solve second order ODEs? In particular, let's solve y double prime minus 5y prime plus 6y equals 0. Now, I will present you a method that's quite intuitive, but a bit slow, and then at the end, I'll tell you a fast method. So to solve this ODE, we will do this by actually factoring out this differential equation. And for this, we need the concept of what's called a differential operator. In particular, when I write dy, I mean y prime, and when I write d squared y, so that's like applying d twice, that's the second derivative, y double prime. And the main thing to notice is that you can actually write the ODE in terms of d, because y double prime minus 5y prime plus 6y equals 0. That's the same thing as d squared y minus 5dy plus 6y equals 0. And the cool thing is you can actually factor out y from this equation. So d squared minus 5d plus 6 applied to y equals 0. And in fact, it makes sense because what is this differential equation? It's differentiate y twice, subtract 5 times the derivative, and add 6 times itself. And yes, I should add the identity operator, but that's okay. And as I said, the idea is now what we want to do, we want to factor out this thing, this d squared minus 5d plus 6. So trick, factor this out. Out as d minus 2 minus 2 times d minus 3. Y equals 0. It doesn't matter which order you pick in. You can also do d minus 3 times d minus 2. And you can prove this rigorously by applying d minus 3 to y, then applying d minus 2 and seeing that it gives you the same result. Now, and what's this good for? The nice thing is using this factorization, we can actually turn the second order ODE into two first order ODEs in the following sense. Because if you let z be the inner thing, so d minus 3y, then our ODE can be written very simply in terms of z, because we have d minus 2 times d minus 3. Y equals 0, that's what we started with, but then that becomes z. So we get d minus 2, z equals 0, which is really dz minus 2z. I hope you're not too dz today. Equals 0. And that's just z prime minus 2z equals 0. And then z prime is 2z. And this is, the infamous basic ODE, whose solution is ae to the 2t. Z equals ae to the 2t. But this is not why we came here today. We came here to solve for y. But remember, we have this definition of y, or of z. So now solve for y. Because what did we have? Z was ae to the 2t. And then z, remember the definition, that's just d minus 3. Y equals e to the 2t. And then this just becomes y prime minus 3y is ae to the 2t, which is another first order differential equation. And this one we can solve using integrating factors. So in this case, e to the at, so e to the minus 3t. So let's multiply this, e to the minus 3t y prime minus 3e to the minus 3ty is ae to the 2t e to the minus 3t. Again, the left-hand side becomes a beautiful derivative. E to the minus 3t y prime is ae to the minus t. And then e to the minus 3t y is integral of ae to the minus t, which dt, which antiderivative of e to the minus t is minus e to the minus t. So minus ae to the minus t plus another constant, let's call it b. And then last but not least, we can multiply by e to the 3t. So minus ae to the minus t plus b. And we get y is, I think, minus ae to the 2t plus be to the 3t. But last but not least, just for a cosmetic fix, since a is arbitrary, so is minus a, and we finally get our solution. Y is ae to the 2t plus be to the 3t. Ta-da! So that's the intuitive way. No, but of course, a little bit slow. Now what I want to present you is a faster way. But I did want to remark one little thing. So for first order differential equations, we had one constant, c. Now, I think here it makes sense that for second order differential equations, we have two constants, a and b. So that will usually be the case. Now, here's a faster way. Because notice, we do have those two exponents, 2 and 3. And you may wonder, where do they come from? They actually just come from factoring out the differential equation. So exponents 2 and 3. Where they come from? Simply factoring out d squared minus 5d plus 6 as d minus 2 times d minus 3. Minus 3. So there they are. And in fact, this equation is so important, this is called the auxiliary equation. So definition, the auxiliary equation of our differential equation, y double prime minus 5y prime plus 6y equals 0, is simply r squared minus 5r plus 6 equals 0. So usually it's d squared minus 5d plus 6, but you will see it's more common to write this in terms of r. So all you do, you replace the second derivative by r squared, the first derivative by r, and then y by nothing. And what's the faster way? It's simply just factoring out that auxiliary equation. So r squared minus 5r plus 6 equals 0. Here you can factor it out as r minus 2 times r minus 3 equals 0. And you get r equals 2 or 3. And using that, you can go directly to ae to the 2t plus be to the 3t. E to the 2t plus be to the 3t. So whatever roots you find, if you find that there are two distinct roots, just put e to the first root t plus be to the second root t. But you have to understand the real reason this works is because of the factoring method above that we just covered.